Isn't it crazy that the only reason we have seasons on this planet is because of the moon? No, that's wrong. Yeah, it is. Yeah, it's because of the Earth's tilt. Guys, the Earth tilted because a planetoid struck Earth. It knocked us off our rotation, and the remains ended up collecting into the moon. The moon is the remnant of that which struck the planet. We would still have seasons, though? No, we wouldn't have seasons at all if it wasn't for that. Other planets in this solar system don't necessarily have seasons. I'm pretty sure that theory has been disproven. Really? I don't think so. How do you define seasons? Okay. Okay. 1 second. Okay. Here comes the sun, I say. It's all right. Here comes the sun. Da, da, da. Okay, there's the sun. All right? So, and here's Earth. Okay? Now we're going to draw the planet's tilt. So this, that's the equator right there. See? This is the equator, okay? Now, the planet rotates like this, but the planet doesn't rotate like this. It doesn't rotate like on the axis that it's with the sun. It rotates on its own axis. What that means is that while Earth rotates around the sun, like in its big orbit, like the big orbit, you know, the different hemispheres of our planet end up getting exposed to more sun. So what we're looking at right now, would be called winter for us. If this is the southern hemisphere, the point that it is in relation to the sun means that the southern hemisphere is being hit with more light. And on the other hand, the northern hemisphere is being hit with less because of the relative exposure of angles to the sun. So our summer is the southern hemisphere's winter, because the opposite effect takes place. If you were to do the opposite and say that this is the position the sun was in relative to the Earth, then the northern hemisphere would get more light and the southern hemisphere would get less light. So that's the reason why temperatures rise during the summer. The summer simply describes the point in the Earth's rotation around the sun where the northern hemisphere is being exposed to a disproportionate amount of light. Does that make sense? Why did you say moon instead of tilt then? Because initially Earth was like this. Earth was aligned in its orbit, but then out from fucking nowhere, from downtown, and then tilted Earth. Then it's not the moon, it was just the planetary crash. The moon was a result of that. Semantics. Look, you can see. Hold on. Mars planetary tilt. Oh, Mars also has a tilt. Oh, here we go. Here are the axial tilts of the planets in our solar system. How interesting. Mercury has basically none. If I'm reading this correctly, Venus spins in the opposite direction of all the other planets, so its tilt is 180 degrees. But it's otherwise basically like aligned. It's just like reversed. Earth and Mars actually have basically the same axial tilt. I didn't know that. That's actually super cool. Saturn does as well. Jupiter doesn't have much of one. And Uranus, for some reason, is drunk? Why is it like that? Wait. Uranus is the only planet whose equator is nearly at a right angle to its orbit, with a tilt of 97.7 degrees, possibly the result with a collision of an Earth-sized object long ago. This unique tilt causes the most extreme seasons in the solar system. Wow. Yeah, what that would essentially mean is that for half of the year, and this is a long year for Uranus. How long is Uranus year length? Year length. 84 of our years, okay? So I want you to imagine the 4 seasons, okay? One of which is Uranus's southern pole pointed at the sun, and the other is its other pole pointed at the sun. Okay? Imagine one face of Uranus being baked at its pole unrelentingly in what would be a 42-year-long day. It would be that long because it rotates at a 90-degree axis. It's not baked because it's super far away. Okay, but you know what I mean. It would be a 42-year-long day. Like, look, Uranus day length. Okay, if you look up Uranus day length, all it does is actually show you how long it takes to rotate around its axis, not how long the sun would remain on some parts of the planet. No, that would mean there are 2 days in a year. No, the planet rotates, but it's like, it's... Okay, it's like this, okay? It's like my Skullgirls plush that I got from my brother. Look, it's a little bouncy. Ignore the arms and legs, okay? Now this is a planetoid, okay? This is a planetoid. The fuzzy hat top is one pole. That's one of the poles. And right here, the anus is the other pole, okay? Now, the way a planet with a 0-degree axial tilt would work is that... Oh, my camera's tilted, so I have to compensate for that. It would just rotate like this. See? Like that. And you guys are the sun. You're facing it from the sun. So all of the planet would get exposed to a roughly equal amount of sun. Now, on Earth, it's tilted, you see. So the tilt means that we have seasons, okay? Now, imagine if it was at a 90-degree axial tilt, meaning that the head was facing you, okay? Now, what would that mean? That would mean this is what a day would look like. 2 days. 3 days. It would keep doing this for 42 years. See? The sun would always be facing this point. It would... Now, slowly, because of the planet's rotation around the sun, it would slowly turn like this. But this rotation, this would be a full year on Uranus. This would take 84 years. An orbit, sorry, not a rotation. This full orbit would take 84 years. The day is 17 hours of ours, but this is what a day looks like. It's just another day, always the sun hitting the same point. Does that make sense? I'm Sin Phoenix. I'm simplifying a little bit, but I'm trying my best here. I'm working with limited tools. Now, the other cool thing is tidally locked planets, okay? And a tidally locked planet is a marvel where the orbit of the planet around its celestial body perfectly matches its actual rotation. So a tidally locked planet, let's say you're the sun, okay? It would be like this. It would be like... The same part is always facing you, you see? Tidally locked planets are the most common type in the universe, theoretically. Yes, because when the stellar dust from whatever came before whatever star system you're referring to all swirled and circled around and eventually coagulated and formed planets and what have you, they would match the orbital rotation of the initial ring of dust. Yeah, the preservation of angular momentum. So on average, it would all settle together. Now, obviously, when asteroids and other planetoids hit, it can knock things off course and it can cause problems. And so the universe is messy, but the underlying principles are, yeah. It's one of the reasons why Saturn has rings, and also why black holes have a ring-like... Oh, what is it called? I'm blanking on the word right now. You know what I mean. It's the accretion disk. The accretion disk, yes. The reason why is because of the preservation of angular momentum. Okay? So, The preservation of angular momentum is basically just inertia, but for rotation. Do I have to explain it? You know, how inertia, a force, if set in motion, will remain in motion unless acted upon by another force? Like, we're familiar with that principle of the universe, you know? Angular momentum works the same way. The energy that is being exerted through angular rotation is preserved unless canceled out or acted upon by another force. So the way I understand it is, why are people in chat being so mean? You guys are mean. I'm not, I'm almost done. Shut up, okay? So, it's fun for me. Oh yeah, this is also the reason why if you're spinning in a chair and you put your arms out, you go slow, but if you pull your arms in, you go faster. It's because there's a relatively, yeah. So anyway, with regards to the reason why Saturn has rings, it's not due to drag. No, because if you pull your arms in, you go faster. You don't just stop. You don't just slow down slower. You move faster. Isn't that interesting? You can literally speed up and slow down and speed up again and slow down. It's wild. Anyway, have you ever wondered why Saturn has rings? I mean, like, think about it. Why would the things orbiting around Saturn form such a neat and perfect disk? I mean, why wouldn't it just be like a really big cloud around it, you know? Well, there's a reason for that, okay? If you take, let's say you're talking about the stellar dust in the universe, all right? You're talking about a nebula or the result of a supernova. You're talking about, like, an unbelievably large amount of mass collected in planetoids and gas and debris and everything, okay? Now, there are several physical features of that collection of matter, okay? One of them is an average overall inertial direction of movement, okay? On average, all of the mass in that big nebula is moving in a direction, on average. Of course, the infinite particles within it are all moving in their own directions, but on average, there is an average direction, you see? That makes sense, doesn't it? You can think of it like, if you have, like, 4 or 5, like, balloons in a room, and you can sort of fuss them all about, you know? While they all go in their own directions, there's an average direction they're heading in, and you can take it by adding up the vectors of all of them, and then you find that eventually you'll find they're going in some direction. Now, the nebula is moving on average in a direction, and because of gravity, they tend to stick together, all these disparate pieces of mass. But it's not just inertia that preserves itself, it's also angular momentum. Now, this is an interesting product of the fact that we live in 3 dimensions, okay? Angular momentum, which causes things to rotate, imagine the infinite particles in a nebula with an average rotational direction, an average axis around which they're rotating. Does that make sense? Like, when I say that, can you perceive what I'm saying? That of all the limitless number of particles, all the atoms and molecules and planetoids and everything, they're all rotating at least a little bit, and there is an average rotation. And you could form an axis. If you somehow knew all the info in the universe, you could cut that nebula right down through the middle and put a pole through it, and that pole would be the average place that they all rotate around. Yeah, kind of like a line of best fit. Now, here's the thing, okay? When this mass starts to combine, when it crashes together, when planetoids and stars are formed, and what have you, if everything is rotating around a given axis, on average, what happens to all that disparate matter when gravity pulls it together? Well, it compresses in every direction, but the rotation gets preserved. And when you preserve rotational energy and then smush it along the horizontal axis along which it's rotating, you make the ring smaller and tighter, but you preserve the ring. Whereas if you crush down on it vertically, as is the case with eventually any gravitational system will cause this to happen, you create a disk. You see? The reason Saturn's rings are so perfect is because we live in a 3-dimensional space. Gravity in millions and billions of years has taken the average rotational momentum of the ice and the other stellar dust around Saturn, flattened it into its average axis of rotation, and then everything that remains is just the product of those processes. Gravity took rings out of infinite chaos from nebula. Now, I think that's pretty cool. I'm sure that there's elements of that I oversimplified or didn't get perfectly, but I'm very, very confident that that is indeed why Saturn's rings are like the way they are. Can you walk on Saturn's rings? They're not actually a solid ring. It's basically just an asteroid and comet belt that's so perfectly refined that it looks like a ring from this distance. I mean, you could walk on the ice and the rock. You could do that. It's ice. It's mostly ice, I think. There's rock as well. I'm seeing if I can get a close-up of Saturn's rings. God, they're beautiful. So pretty. And all a product of a just wild natural process. The conservation of angular momentum. This is from NASA. Yeah, there we go. Here are a couple of prominent, I'm assuming asteroids. Look at that. Look at how distinct these rings are. We're talking, on a planetary level, we are talking about an unbelievable amount of precision in the construction of these rings, you know, as though, I don't know if this is a photo or a mock-up. That looks fake. Yeah, I don't know if we've ever gotten a camera that close. It's so cool, though. A little ballerina planet with its ring. Oh, yeah, the rings are still many kilometers thick, of course. They are not in any way, shape, or sort of small, just relative to their width. I mean, these are like 100,000 miles wide or whatever. Kasani Pictures. Oh, man, is this a photo? Wow. Is this a photo? Kasani top 10 images? Oh, my God. Look at the unbelievable precision. This is again from Kasani. Cassini? Cassini, sorry. And all of it is a product of natural processes that you can observe and recognize in your day-to-day life. Spin a chair, pull your arms in, pull your arms out. It's the reason why ice skaters, when they want to do a spin, pull their arms together as tight as they can. Can you do the chair thing? No, this chair is huge and heavy, and also the wheels that allow it to rotate are not in the best shape. Why does it smoosh together like that? The rings? Look at the hexagon. Yeah, Saturn's hexagon is pretty wild. Didn't CGP Grey do a big meme about this? The gigantic, like, Earth-sized storm. That's a perfect hexagon happening at the pole. Yeah, it's pretty weird. I don't know why that's happening. I won't pretend to understand the motivation there. Wow. Look at this. NASA pics reveal huge rose hurricane on Saturn. Whew! I assume it's been colored after the fact, but yowza. That is not a part of the universe I want to be in. That looks like some rough storms. Oh my God. The spinning vortex of Saturn's North Pole storm. Oh my God, look at this HD image. Wait, this is real. Holy fuck. This storm vortex is the size of, like, how wide is it? Hold on. I want to see how wide the vortex is. Saturn Rose Vortex size. Image scale is 1 mile per pixel. All right, guys, here you go. 1 mile per pixel. That's NASA, by the way, that said that, not me. So that's on them. Yeah, this looks like a fucking warp storm. It's estimated 18,000 miles wide. How wide is our planet? Okay, no. The Saturn's hexagon is estimated to be about 9,000 miles long. Okay? 9,000 miles for the whole hexagon. Earth is about 4,000 miles long. No, wait, that's our radius. I'm sorry. So 8,000 miles long. My apologies. Wait, no, it says the sides of it are 9,000 long. Wait, my bad. Why wouldn't it say the diameter? I assumed it would give me the fucking diameter when I asked how. Okay, the hexagon is 20,000 miles in diameter. Earth is 8,000 miles in diameter, meaning that the total hexagon could fit like one Earth here, and then one Earth here, and then like a remainder, you know? And then you have this in its center. Okay, this thing is apparently 1,250 miles across. Which is how big? Let's see. Let me see if I can find a state that's big. What? Length of Texas. Okay, it's bigger than Texas. Length of Alaska. About 1,400 miles north to south and 2,500 miles east to west. Okay, guys. So I think that if you ignore the frilly bits at the ends, this is about the size of the storm. If it was on Earth, it would be raging basically from the northern tip of Texas over to, like, Minnesota. No, we're not talking about the hexagon. We're talking about the rose center. This fucking thing. The coolest part, you know? So, yeah. This seems like, I'm just guessing here, but I have a feeling that the winds and the temperature inside of this storm, along with the electrical currents, would probably not just kill everyone in the Midwest, but would also strip the entire, like, crust of the Earth. You know what I mean? I feel like somehow transporting this hurricane onto the Midwest would be like, yeah, it would be like the equivalent of like, dropping nukes with just the total amount of energy being deployed. I want to know one more thing. Do we know the wind speeds in there? Saturn Red Storm. Rose Storm? Okay. Saturn Red Storm wind speeds. Hit me up. At the edge, wind speeds reach 270 to 425 miles per hour. That's more than twice the speed of even the strongest hurricanes on Earth. Okay. Yeah. At the storm's center, winds are relatively calm. Oh, no, wait. This is for Jupiter's Great Red Spot. Hold on, never mind. I'm sorry. This is a different gigantic storm that's 6 times as wide as Earth is. Hold on. I want to know about Saturn's red spot. Hold on. All right, there are some cloud speeds as fast as 330 miles per hour being recorded in the Rose Storm. Which, quick question, guys. If that's what we can see on the surface, what do you think it's like beneath the surface? I mean, we can see the cloud movement on top, but makes you wonder.